In today's session, we are going to see the concepts of divergence. In the applications of Gauss law, we have discussed the vector of flux density should be made constant or to zero. In the previous sessions, we have discussed the same for a point charge and for a line charge. As we all know, there are two charges available, one with a positive charge and one is a negative charge. The field moves outwards for the positive charge while the field moves inwards for the negative charge particles. In today's session, we are going to see the divergence due to charge particles. To understand this divergence, we take a very simple example of waterfall from a tap. So again, as we can see in the video, the water falls from the tap, and when it reaches the basin, you can see the water is diverged in all the direction. So this is what we are going to analyze in our charged particles. Again, the waterfall is also in the three-dimensional coordinate system, and what we are going to analyze is also in the three-dimensional coordinate systems. So let us convert this water flow into the equivalent vector representation. This will give us a easy visualization, and we can easily solve in the point charges also. So this image shows the vector equivalence of the water flow. All the blue lines is going to represent the velocity of the water from the tape towards the basin. So for my simplicity, let me have a cube. Thereby I am going to analyze where the divergence is, whether there is a divergence of water is there or not. Now if we place the water on the vertical axis, we can see the cube, whichever water comes inside the top surface will leave at the bottom surface. That means it is not deviating from its point, it goes exactly in the straight line. So there is no divergence is there. But if we keep the cube at the surface of the bottom or at the basin surface, we can see the water hits the bottom surface, and the water deviates in all the direction. So now our point is to calculate how much it is divergence happens in the water flow. So to understand this, let us represent the water flow in a mathematical model, so that we can easily visualize the things and we can move forward. Now let us see how we can use a mathematical model to find the divergence of water flow. To do as a mathematical point of view, let me convert the velocity of water in terms of vectors. So all the blue arrows in the diagram is going to represent the velocity of the water. So for my simplicity to visualize, I am going to take only one vector and I am going to do the animation here. So I can see it travels from the top of the tip of the tape, and it follows till the bottom of the or till the surface of the basin. So once it touches the surface of the basin, you can see that the water is going to diverge in all the direction. So the divergence is represented in terms of red color lines. Now let us try to calculate the divergence of a water flow. So to find the divergence, so let me take an imaginary surface, just as we have shown in the previous video, of a small cube on the flow of water. So here the water flow comes from the top and it moves to the down. So you can see that it enters at one surface and it is diverged in all other surfaces, or in the sense that it is coming out in the remaining 3 or 4 surfaces. So now we can see, if you take the sum of all the surfaces, we can see how much the water is diverted in each direction. For the surface, again we are going for a 3 dimension for the water. The same thing will apply for our charged particles also. The imaginary surface for the water seems to be convincing for us. Now let us focus to our uh, charged particles. So it is easy for us to visualize for the water. Now when you look at the charged particles, as we have seen, there are 2 points are there. If it's a positive charge, it's going to be a source, that means the electric field will be moving outwards. If it's a negative charge, the electric field will be moving inwards. So let's assume that now if we want to find the divergence, how much it is deviated from the source in all the directions, what I can do is I just can use with the help of the Gauss law, and I can find the flux density which is available in all the surfaces, so that I can easily find whether it is diverging or converging, or there is divergent less movement is there. So from the Gauss law we can tell that if I know how many flux lines are passing through it, I can find what is the charge. So let us assume that my charge is a positive charged particle, and so it is also called as a source. So let me create an imaginary surface around the positive charged particles as shown in the video. So as you can see that as we move on, I am going to take a Cartesian coordinate system. So I need a cube to have a proper enclosed surface, or you can call it a contour. The charge is present at the middle of the cube, that is from each side. The distance between the front and the back, if we take as a delta x, the charge is present will be in the delta x by 2. So this was the simple animation is shown here. At the middle of my cube. So for my analysis, I am going to take from the Gauss law that the integration, so I can say that integral closed integral of vector d dot to the differential surface is what I am going to take. So here if you look at, I am going to have a 6 surface. The surfaces are, so what are the surface I will be having will be of, so I will be having a front, I will be having a back, I will be having a left, I will be having a right side, top and bottom surface. So these are the 6 surfaces I will be having right now. So as I know that the Gaussian law, if I am going to do these calculations, then this is for the surface. So I need to calculate for the 6 surfaces, then I have to sum it. So finally if I sum the value of this all the surfaces, then I can find how much divergence in a volume, I can find how much divergence can be available. Okay, let's start to deriving each and every surface first. Let me go for the front surface. Okay, so in a front surface, if we take the front surface, what are the assumptions we are going to have? So this is nothing but there is a differential with respect to y, and this is differential with respect to z. Okay, and I am going to, the front side is, this is the front side for me, so this is the front side. Okay. So where is my charge available here? So if I look, the charge is available for me, it is on the middle. So if I extend this, okay, so this is the midpoint if I am going to have. So I know that this distance is also equal to del x. So there's a small changes there. So it is in the middle. So I can say that my point is at delta x by 2. Okay. So if I want to find the surface interval, so when I looking at the x-axis, I can see that there's two surfaces available. One is a front, so there's a front surface I have to solve, as well as the back surface. So both the things I have to solve. So first let's concentrate on the front surface. So if you're going to concentrate on the front surface, I know the x is fixed, so I can write ds del y, so that is a y-axis which we are seeing here, into there is a change with respect to the z-axis, so I can write it as a del z. So if I have a change, my normal to the vector is pointing towards the positive x-axis, so that is nothing but a x cap. Okay, so I'm just typing it out to make it clear. So it is a del, there's a small change of, there is a triangular shape, is a del y, del z and a z cap. Okay, so similarly, so I have to find for the other vector. So we'll keep it here. Similarly, let me find, so what is the value of d? So d, the capital D, is given as, so what we are focusing is all about is the front axis. So in the front side, what we have is d front is what we are focusing, and it is in the direction of the positive x-axis, so I can write it as dot, I have again ax cap will come into picture. So what is d front here? So I can write d front as I can say from, what is the d here? D is nothing but with respect to the x-axis, I can write dx. Okay, so from there I will take ax caps, not avoid the confusion. So let me take will be of d into dx ax plus, do I have, does it completes everything? Yes, my charge point is here, then I can say that the charge is available, but I am calculating the flux density, but the flux is also changing with respect to the x-axis. Okay, so I can write it as, is it a positive, the location is at the positive, so I'll write it as x, so del x by 2 into the rate of change into the rate of, so again I'll be having into the rate of change in x. Okay, so this is the scenario, this is what we'll get into picture. Right, so rate of change with respect to next. Okay, so this gives us a clear picture for us what is the equation we have to write here. Okay, now we can say del x ax, this we are taken from this equation, del x divided by 2, because this is the part we have to work out to understand this thing. So we have that surface, the surface is available for us. Okay, so this is the surface that we have. So let me choose this. So this is the surface I am focusing, but what I want is, I am calculating the electric flux on this direction, right? So I am calculating how many flux lines coming on the front surface. So this is what we are going to concentrate, but unfortunately our point charge is at the middle. That's the assumption we do. So my surface is away, the distance away from is a del x by 2, and the flux is changing in the x direction, so both are in the positive x directions. So that's why we are written. So if I do the, if I implement this in the Gaussian surface, then I can write the front as, so integration of front, I can write it as, so here ax and this ax, when I do the multiplication dot product, so it will end up equal to, the value is equal to 1. So now we are end up in a scalar quantity, and all this towards the positive x axis. So I can write it as dx plus, so delta x by 2 into partial differentiation with respect to x axis. So this is what then this is for the first surface. So for this ds, so I'll get delta y and delta z. This is for the front surface, which I got from the equation. Now what happens if I go for the back surface? Okay, if I go for the back, so here when I go for the back surface, we have to understand that this is away from the x-axis, that is, it is actually in a negative side, the negative of my x-axis. So this is the positive side of my x-axis, so it is on the negative side of my x-axis. So what happens here is, here this will be equated into minus delta x by 2 into the rate of change with respect to the x. So it will be that. Now what happens to the surface here? Will it remain the same as delta x delta y, but the direction will change. So this I can write it as delta y and delta z minus a x cap. So if I substitute all this here, then I can write, so integral at the back, I can write it as, so here what we have is again the same parameter, ax will become 1, so I can write it as, so dx minus delta x by 2 x axis dou by dou x. So this is what I'll get, the inner dot. So here what I have is minus delta y and delta z. Dx delta x by 2, so dou by dou x delta y and delta z. So when I add these two things, the front surface, integral of front plus integral of back, so what I will end up is, so my dx term and dx term will get cancelled, so I will end up with delta x dou by dou x into delta y and delta z, so which is nothing but I will be having the partial differentiation of dou by dou x, so into delta x delta y. Now I can rename delta x, delta y, delta z as delta v also, so which in turn it gives me the partial differentiation partial differentiation with respect to x delta v. So this is what the result what we got when I do the summation for front and back. So similarly we will get for the will be with respect to the z axis, so the differentiation will be with respect to the z. So when you go for the right and left, it will be with respect to the x. So I am leaving you that as your to work out to derive on your own. So we'll discuss, if you have any issue, we'll discuss in the classrooms. Do the okay, now if we do all this analysis, so finally we will end up in a integration, so closed surface of ds dot differential element of differential surface will end up into parameter of dou dx, that's the x component, the rate of change which we have told with the partial difference with respect to the x. I think in my previous lesson I have not added this dx, so I can add that. So dou will end up in dy divided by dou partial rate of change with respect to the y, as well as I have dou into dz divided by dou z, and I am having a volume of del v. So this is the expression which we have got. So after deriving everything, this is the expression we'll get. So you know that the closed surface integral of the vector d to the surface differential surface element, so I'll get dou by dx, dou dx divided by dou x plus dou dy by dou y plus dou dz by dou z into the volume. So this is the key parameter. If I do the integration on the surface, I can actually find the volume. So this is a major difference. But in order to find the divergence, so what's the key factor here is, we have to make sure that this ds is with the dot product of this has to convert into a constants. So in order to make sure that this has to be a constant, I have to make sure that dv tends to 0. So if I apply the limit del V, that's a volume, has to tends to that means it may as small as possible. I cannot take the bigger volume, it should be as small as possible so that I can calculate the value. So if that is the scenario, so I can rearrange this equation as, so I can say the integration, surface integration of d, let me write like this, so ds divided by del v. Del v, I can write it as, so this entire term will come into picture. So this everything is nothing but is a partial differentiation. So this, okay, so this entire term I can name it as nebula on the del operator. So remember, this is different, this is a small difference is there, so this entire partial difference I can name it as a nebula operator. So I can write it as the dot, so again the d I can take it as outside. So remember, this is the dot product, so in other terms only the partial difference. So let me write it here. So nebula operator is going to represent only dou by dou x plus dou by dou y plus dou by dou z. Okay, so this d, if I take dx plus dy plus dz, so anyway I'll end up in the same combination of vector equation of theta. So what I can tell is, so is nothing but if I have a del dot d as the divergence, so which is equivalent to, I can say, integral again d, the closed integral for ds, provided the volume element tends to 0. So this is the key for us. This is called as divergence theorem. So in some textbooks it is also this parameter. I can also write it as divergence dot d. Remember, this variable is vector. So you are doing the dot product of the vector also. So with the partial differentiation in all the three direction, I can end up in the surface integral in all the things. So both you will get the same results. So we'll be solving some problems in the classrooms. So be ready to understand these concepts and we can verify this theorem.